So this is our last set of reactions for chapter 22. We're going to learn 3 reactions in this section. These reactions together are called the conjugate addition reactions. And I feel like these reactions are probably not the most difficult reactions that you've looked at this year, but they're hard reactions. The good news is that chapter 22 is really the end of the hard stuff for this class. And we only have one more chapter left, and it is significantly easier than anything we've done this whole quarter. And so you're almost all the way through the tricky stuff. So, like I said, there's going to be 3 conjugate addition reactions that we're learning. The first one is called the Michael addition reaction. All 3 of these reactions are pretty new in terms of the history of organic chemistry. And so the Michael addition reaction involves a conjugated, usually alkene with carbonyl, like something like I've drawn here, where you have a carbon-carbon double bond that's conjugated with a carbon-oxygen double bond, but I'm going to show you a few varieties on that. And it's going to do a 2-step reaction. It's going to react with a weak nucleophile. I'm going to give you a list of what these nucleophiles are. And then H3O+. And what we're ultimately going to make is just usually a carbon-carbon bond. We're adding the nucleophile to that last carbon of the conjugated system. I want to highlight the conjugated system in these reactions. So if this is our conjugated system right here, these are the same atoms that are part of that conjugated system. And when we were doing addition reactions to dienes in the winter quarter, and we were doing 1,2 versus 1,4 addition, you learned this numbering system, 1,2 versus 1,4, where we number the 4 carbons of the conjugated system. Has nothing to do with the way we would number a molecule if we were going to name it according to IUPAC. This is just finding those 4 atoms that are part of the conjugated system and numbering accordingly. So in this Michael addition reaction, we are technically ultimately adding this. So we're going to put a hydrogen. There's 1 hydrogen on carbon number 2. We're going to put another hydrogen on carbon number 2. So technically we're adding to these 2 sites. Nucleophile goes on to what I've labeled as carbon number 1, and a hydrogen goes on to what I've labeled as carbon number 2. If you're looking at this reaction in your textbook, you will see that it actually passes through an intermediate, which this is going to look a lot like 1,2, 1,4 addition that we learned with dienes. So initially, this is a 1,4. Technically, we're adding the nucleophile to carbon number 1 and the hydrogen to oxygen, which is number 4. And then that intermediate tautomerizes itself. Which just means, remember, that just means that we move the carbon-carbon double bond up to become a carbon-oxygen double bond. A hydrogen gets shifted, in this case, from oxygen 4 down to carbon number 2. And the motivation behind that is just stability. The carbon-oxygen double bond is more stable than the carbon-carbon double bond. So your textbook is going to really focus on this reaction, going through this enol intermediate and tautomerizing, but it's totally fine if you would prefer to just ignore this tautomerization thing and just focus on the 1,2 addition aspect of this reaction. If you just really focus on this part right here for the sake of just keeping the reaction as simple as possible. So what I want to do is show you in your textbook, you have a table table 22.2, which is somewhere around page 1080. In my book, it's on 1081, so it's somewhere in that area. And this is a list of the most common, so notice this emphasis on this is common Michael donors and Michael acceptors. Michael donors, this is just another way of saying that these are the nucleophiles. And then the Michael acceptors are the reactants, the things that the nucleophiles are adding to. So when you're doing these problems on sapling, you're going to see the same general structure for the donors and the acceptors. The difference is that sapling is allowing for a little bit more variety in these structures. So it's not just limiting, for example, it's not just limiting the diester here to an ethyl ester. It could be any OR group coming off of this. So you'll see a variety there. Or over here, these could be larger R groups than just methyl groups. So just sort of be open to the possibility that these carbon chains could be bigger than what you have in your textbook. Sapling is not varying by much in really just the larger R groups. The one thing that you will always see with the donors and the acceptors is this consistent, for the acceptors, this consistent conjugated system. That's always going to be there. That much of it is never going to change. And then for the donors, you're always going to be seeing, again, this like side to side, separated by just one alpha carbon, double bonds, or in this case, it's a triple bond, something along those lines. So there is a definite pattern to the structure of the donors and the acceptors. So let's look at a reaction and the mechanism. The problems that you have on sapling are going to ask you to fill in curved arrows for the mechanism. So you're not being asked to predict any products. You're just being asked to walk through the curved arrows and just kind of draw the structures of intermediates. And so we are going to use, for our example, we're going to use this guy as the acceptor, and our donor is going to be this guy right here. And the first thing that I want to do, because this is going to be the first thing in these mechanisms in sapling, the first thing that I want to do is show where this nucleophile comes from. Like this guy right here is our nucleophile. So I want to show where that nucleophile comes from, because that forming the nucleophile is going to be part of your problems on sapling. The nucleophile is formed from just a regular dicarbonyl, diketone, diester, whatever it might be, and a strong base. It could be a hydroxide, it could be a methoxide, OCH3, could be an ethoxide, OET, just some sort of strong base. And whatever that strong base is, it's going to grab that double alpha hydrogen in the middle of the two carbonyl groups and form that nucleophile. So that's where the nucleophile comes from. I'm going to erase this part. Once the nucleophile gets formed, the nucleophile itself is going to attack. Let's remember, we want to focus on the conjugated system. And I'm going to put some numbers on those the atoms so that we can talk about them. 1, 2, 3, 4. And again, this has nothing to do with IUPAC numbers. So the nucleophile is going to attack what I'm labeling as carbon number 1. The electrons in between 1 and 2 are going to move so that they're in between bonds 2 and 3. And the electrons between 3 and 4 are going to move out onto the oxygen atom. So what we're going to get here is going to be kind of bulky when we draw it. But we want to make sure that we're getting all the atoms in the correct order. We're not going to worry about if it looks good. Oxygen now, because we moved electrons up onto it, has a formal negative charge. We put, let me fill in my numbers here, 4, 3, 2, 1. We put a double bond in between carbons 2 and 3, so there's that. And then to carbon number 1, we created this bond with the nucleophile. So let's draw the nucleophile in. And just make sure that you're not losing any carbons or adding any carbons. So there's that. And hey, we made a carbon-carbon bond. And then the next step, which, I'm going to draw the next step of this reaction to match exactly what sapling wants you to do. This is going to look a little different than what your textbook has, and it may or may not look different than what like Khan Academy might have, but this is what sapling wants you to do. So that's what we're going to draw. The next step, so this is step 2, where we bring the acid in. I'm going to draw H3O+. So what happens in this step is that the a lone pair of electrons on the oxygen will come back down to make a carbon-oxygen double bond. And the double bond in between 2 and 3 is going to get protonated by the acid. And so what we will end up getting is carbon-oxygen double bond has been formed again. That carbon-carbon double bond that started out in between 1 and 2 and then moved in between 2 and 3, that carbon-carbon double bond is just gone. It's not there anymore. We have gotten rid of it. We added that hydrogen from the acid. There was already one hydrogen there, so that's the product. And again, this mechanism is pretty simplified. The actual mechanism, if you were looking at another resource, is going to take you through the tautomerization process. You're going to ultimately get the same product, but the way it's drawn here is exactly the way sapling wants you to draw it. So before you do anything else, go straight to sapling. Do questions 14 and 15 because it's asking you to draw these mechanisms.